All right. Let's see how far we get before I crash, because it is about to be 11:15 tonight. We're gonna start. This is the last lesson, or at least part of the last lesson. We're gonna start with hypothesis testing, and the very first thing we're gonna do is we are going to state the null and alternative hypothesis. Now, the idea is we have a question that we want answered, and that question is the data giving me sufficient information to suggest something is changed? And that's the question we want to ask. Now, this question, let's just give you an idea of what the question is going to be. In 2008, 60% of American adults regularly volunteered their time for charity work. Researchers believe this percentage is different today. Has something changed? Do people give more or less? Okay, is there more percentage of adult Americans volunteering, or is there less percentage of adult Americans volunteering? Okay, has it changed? All right. Sometimes they specifically state what they believe. So according to the study published in March 2006, mean length phone call on the cellular telephone is 3.25 minutes. A researcher believes that the mean length of call has increased. So they think specifically that it's increased. And then using an old manufacturing process, the standard deviation of amount of wine put in the bottle was 0.23 ounces. With the new equipment, the quality control manager believes the standard deviation has decreased. So here again, we have kind of three options. We have either we believe there's an increase, we believe there's a decrease, or we don't know, but we don't think it's the same. Okay? And here's how we're going to state these three different options. Let's go back here. I'm going to write it on here. I'm going to go ahead and tell you that was that thing. I'm going to go ahead and tell you that there's been some differences of opinion on how to state the null and alternative hypothesis. Now, the null hypothesis is where everything is different. That's where people have a different opinion. But the thing about this is every time you answer this, every time you find the null and alternative hypothesis, you're actually going to find the alternative first. So we'll just say the null hypothesis is the status quo. You know what I mean? And hopefully I'm using that word correctly. I think I am. Basically means it's what it is. It's the null hypothesis is everything's the same. Okay, no changes. Okay, no changes. The alternative hypothesis, okay, is that there is change of some kind, whether an increase, decrease, or we just don't think it's the same. All right. Now, here's the problem most people have with this. You're actually going to find the alternative first. The alternative is what's specifically written in the question. Okay, in this case, not so much because they don't know if it's an increase or decrease. They just think it's different. So my alternative hypothesis, and we'll just write this as H1. I think this book uses H1. Again, books, I've used several different books, and some use H sub 0. All right, and H sub 1, where this is your null and this is your alternative. Okay. So I've had other books use H sub A. Don't remember what this one does. Let me see what this one does. Oh yeah, this uses 0 and 1. So here, since this is a proportion, so either this is going to either be a proportion, a mean, mu, or it's going to be standard deviation. One of those three. Now, the status quo is that proportion is 60 2%. These actually should be equal ones, not equal. What they believe is that it's different. Now, different means that it's no longer equal to 62. So this is your null and alternative hypothesis. The status quo is that it stays the same. The alternative is that it's different. Let's look at the next one. All right, so here, status quo is 3.25. So the null is that the mean length of time, so mean u is equal to 3.25. They believe that it has increased. So the alternative one is that the mean has increased. And that's your null and alternative hypothesis. Here, the manufacturer believes the standard deviation, so now it's standard deviation, so our null about sigma, and our null alternative is about sigma. These will always be the same, by the way. Status quo is that it is equal to 0.23, and they believe that it's decreased, less than 0.2. And that's really all you're going to do for your null and alternative hypothesis. Now, the not so nice thing is you're going to be given more than just one number, right? In the question, what you have to do is figure out what is the population. What's the assumed population value? Notice that none of these were p hat or s or x bar. These were all population symbols. For u is pop mean, proportion, that is population proportion, and sigma, that is pop standard deviation. These are all population symbols. These are not sample size, so you have to make sure that you're not sample data. I don't think it's going to come up here in 10.1. 10.1. 10.1, by the way, you're gonna notice I kind of I deleted some things. I just want you to be able to find the null and alternative hypothesis. The rest doesn't really matter until the end. I'm not going to have you find the type 1 or type 2 errors because that's just a pain to find. Type 1 is not a problem, but type 2 errors. So I'm not going to worry about that. All right, so again, hypothesis. Null, again, is the statement to be tested. The null hypothesis statement of no change, no effect, no difference. It should be true until evidence indicates otherwise. In this chapter, it will be the statement regarding the value of the population parameter. In H1, a statement that we're trying to find evidence to support. In this chapter, it will be a statement regarding population. Again, same thing. So either it's a two-tailed test, which means we don't know if it's greater than or less than. That's two-tailed. We don't know greater or less than. So we're going to do either or. Or it's going to be a left-tailed test, which means less than. Right-tailed test, which means greater than. Now, to be honest, here's the really nice thing. Since we have R, left and right-tailed tests don't matter. In fact, most of this doesn't matter what kind of test it is. Two-tailed tests are specific, so that is important. Basically, you need to know if it's a one-tail, right or left, or a two-tailed test. You do not need to know if it's left-tailed or right-tailed because the way we do R eliminates the need of that. Okay. All right. Moving on. I did use that status quo. Right. Okay. I'm proud of myself. I used the English word correctly. Languages. Anyway. We did all this correct, so we're good here. Okay. Now, again, that's just stating it. So you're going to see on the notes this. That's not what I'm on. There's chapter 9 again, if you remember that fun thing. Untitled 1 here? Yeah, chapter 10. Let me see. Thought I saved it. Chapter. Save. So most of chapter 10, if I give you anything, honestly, I don't even know if I'm going to give you questions out of the book. I will. I guess I have to. I remember looking at it. I have to for some of them. So yeah, I will be questioning it, but I don't know if I'll give you anything out of 10.1. I may just skip to 10.2 and 10.5. We'll see. I don't know how far we're going to go down that road, okay? All right. So you're going to see that you need to make the statement, and this is how you're going to make the statement. Okay. This is a you don't have to tell if it's a right or two. You just need to know from the statement if it's a 1 or 2 tailed test, because that's going to be a big difference. So back here, yeah, there's no R value for this, just you typing it in. Okay. This is where we start to use R when we actually try to do a hypothesis. Here's the thing. On every one of these, there are 2 ways to do the hypothesis test. And we spent the last few chapters figuring those ways out. Remember chapter 8, which was sample distribution and t-distribution, finding probability, probability for proportions, probability for mu if we knew what the standard deviation was, or probability for mu if we don't know the standard deviation. So again, if you remember chapter 8, back here, or right here. So probability, proportion test. No, it wasn't probability. All this right here. Front test, value. We're basically looking for value. Oh wait, no, this was proportions. That's right, that's proportions. Chapter 7 and chapter 8. Okay, that's right. I remember this from just 2 weeks ago. I miss being in class. All right. Right back here. Okay, so we did finding z, and then we found area, and then we find probability. So basically, chapter 7 was finding probability. If we knew what sigma, or we knew what the standard deviation was, finding probability. If we didn't know the standard deviation, finding t-distribution. Not do t. Only do t. Okay. Okay. What was the first introduction to chapter 9? Oh well. Okay. So we'll look at how to find probability for t. So hypothesis test. Then we have here's how you do your t test. Again, we'll get to this in a moment. This is 9.2. 9.2. 9.2. 9. Sorry. 10.2. I'm already starting to crash. 10.2 is Z. And then we have 0.3 T. Then we're going to have down here 10.4, which is going to 0.2 Z distribution. Which basically means sigma is known, so we know the population standard. Then we had 10.3 T distribution. Means sigma unknown. And that may be as far as we get today on this. I may do 10.4, which is portions. That may be how you spell that. Then we have 10.5, which is back to standard deviation, chi-square. So now, for all of these, like I said, as I started this whole, for all these, there's two ways to do each of them. We can either find probability, and we compare the probability to what's called the level of significance, or we find the confidence interval, and we see if the true mean, the given mean, the assumed value, is inside the confidence interval. Honestly, I don't really. I think I'm going to specifically state which way because you need to know how to do both. But honestly, I think the easiest way is the confidence interval. It's so much easier to explain. But that's fine. That's fine. We'll do both. I'm going to pause and hopefully my mic is working. If there any issues, can you all hear me? Not like I'm going to know until after this video is done, but still. Alright. So I paused for a bit. Time right now. Make sure. Here, first thing, at my and I'm going to do these ways. If you are, it doesn't matter how you do. It's going to be the same way each time. So here I've done. This was from the PowerPoint. So I have a can of 7 Up 5. So that's the quality control engineer worry the filling machine. That means they don't know underfilling or overfilling. Selects 9 cans. Data. Use the p-value approach to determine the point to claim. Prior experience indicates that sigma is equal to 3. The first thing you have to do is process. Pretty easy. Back up here. Now here I actually did this two ways because I wanted to do this both. Being that 355 was all these values, all but 2 are all at 355 or under. The rest are over 355. I was assuming that it was overfilling. Assuming that it was doing. So I'm going to just say, instead of worrying about overfilling, I want to do a regular instead of before we start doing editor. So here we're just going to assume it's overfilling. All right. So first we have to find the p data. P value is still going to be the same way we did before, Z1, because the first question is the mean of the data of the. I named it 7-Up at soda. You have to type in the word 7. You can't use numbers because it messes with it. It doesn't like using numbers as names. 7-Up $.10 soda minus the mu minus the expected value. Again, finding your regulars. Now here's a big plus. Here's what you're going to want to do every time for Z distribution. Okay, you're going to find the probability using p norm of negative absolute value. The idea is you always want your z-score to be negative. It makes it so much it's negative. This means we don't have to worry about right tail test, left tail test. This is what I'm talking about. We don't have to worry about right or left tail test. And this is why. If we always do it this way, it'll work out very nice. Okay, I don't have to worry about right or left tail test because no matter what, it is making it, kind of forcing it into a left tail test, which is calculate. So I get this probability 0.059. So I'm just going to go to 4 decimal places, 0.0591. 0.0591. Now here's the test. Is this less than the level of significance? So this is that level of significance. Is it less than the level of significance? Is this 0.0591 less than 0.05? No. Actually, it should be false. False. Okay, which means we fail to reject. If it's false, we fail to reject. If it's true, we reject the null hypothesis. Now, this is that final statement, and this is the statistician's way of saying everything's fine. It's not over. Okay? But you're going to see results down here, and it's here's how you can label results. Anytime we fail to reject, you're going to say there's not enough evidence at whatever level of significance. Just the machine is doing something different. In this case, the machine is overfilling the cans. Not enough evidence. Now, here's the difference between a one-tailed test, which is what we had on one-tailed test, less than or greater than is a one-tailed test. But if it's a two-tailed test, if it's not equal to, that's a two-tailed test. So this is number 2 here, two-tailed test. Same question, same setup, nothing's changed. This is the difference. That's the difference of a two-tailed test. Before, back up here, you see P norm of negative absolute value of your Z. Now I have 2 times P norm of negative x. So basically it means you have to multiply your probability by 2. And that's what we get, which we rounded to 4 decimal places. And obviously it's false. Okay. So we fail to reject the null hypothesis. And there's not enough evidence at the 0.05 level of significance to suggest the machine is not filling the cans correctly. Right? So that's your Z-test. All right. Now, if we're given the sample mean, we can just type in the sample mean here. We don't actually have to find it. We can just type it in. That's real nice. Now, the last way to do this, part 3, is confidence intervals. And here's the nice thing about confidence intervals. It doesn't matter if this is not equal to, if it's a 1 or 2 tail test. It doesn't matter. 1 or 2 tail tests do not matter for confidence intervals. Could be greater than, could be less than, could be not equal to. Makes no difference. So we first set up the null and alternative hypothesis, and then you do the confidence interval, just like we did in chapter 9, confidence intervals? Yeah, chapter 9. All right. And here's our confidence interval, 354.6 and 358.8. So now the idea is, if the given mean, if the understood mean, there it is, if the value they expect to have is inside the confidence interval, that means we're safe. Nothing's wrong. We reject the hypothesis. There's not enough evidence at the bottom level to suggest the machine is not filling the cans correctly. So as long as this number, the given mean, the test we had at the very beginning, as long as that is inside confidence interval, in between the two numbers, we reject the null hypothesis, which means there's no evidence to support something's different. If that is not inside those two numbers, then we reject, and then we fail to reject. Sorry, this is wrong. Fail to reject. Fail to hypothesis. Sorry, it said fail to reject up here too. So again, if this is within inside the absolute value or our interval, we fail to reject. It means nothing's wrong. If this is not inside our interval, we reject the null hypothesis, and there is enough evidence to suggest it's. Again, that is the 10.2. That's pretty much all you're going to do for 10.2. If they give you all the information, you can just type it in. But if they give you raw data, you're going to have to input it. And again, I just use CSV just because that way it'll work when finding mean or standard deviation or whatever we want, as well as doing confidence intervals, because confidence intervals do not work with files that are not CSV. Okay. Now 10.3, t-distribution. Sigma is unknown. Now what if we're not given any raw data, we're just given all the information. Now I skip down here to do all the way down here. The first question they gave us was, so I skip to the next question where we had raw data. So here, according to the United States Mint, quarters weight was 5.67 grams. Researchers determining whether the state quarters have a weight that's different. Again, this is different. This is another two-tailed test. He randomly selects 18 state quarters and weighs them and obtains the following data. So it's raw data. We just I found this right here. I actually ran the mean, okay, and ran the sample standard deviation. I found those. So let's just say we're given them. Now these are rounded values, so you have to be careful here. Here we have T4, so for T distribution T4, we're rounding this to 4 decimal places. So it's basically like finding your z-score. Here's the difference. We're going to find PT, so that's a probability of T, using the absolute value of T4, comma, 17. Now this is your degree of freedom again. Your degree of freedom is always 1 less than your sample size. Right? Lower equals false, times 2 for the 2-tail. If it's 1-tail, then we just don't worry about times 2. All right. Let's see here. All right. So since the p-value is 0.0202, what they got? Probability was 0.02. Okay, so they round a little more than we did. All right. So since that is less than the 0.05, it is true, and therefore we reject the null hypothesis. And there is sufficient evidence at the 0.05 level to conclude the mean weight of the state quarters differs from 567 grams. So we got true here because this probability was less than. Now you can also do this with raw data. Okay, and in raw data it's so much easier because you don't have to do anything really. You just run this. This is the formula for raw data. Now here's the thing. If this is you're doing less than, you would use less. Go is less than that. If you're doing greater, so less than or greater than, that is important. It's gonna be kind of a key thing here. And then if you are doing two-tailed, you just do two-sided. So 2-sided. That's the difference between doing a less than, greater than, or a two-sided. So it will be important to know if it's less than or greater than, or if it's two-sided. Now again, this one's two-sided. So notice the p-value is a little different, and here's the reason why. There's no rounding here. This does not round anything, so this is going to be much more accurate if you have raw data and you can have R do all the work for you. Otherwise, there's rounding involved, and the numbers will be different. Here we got 0.0136, so since that is less than 0.05, it is true. We reject the hypothesis, and again, there is sufficient evidence at the 0.05 level of significance. Include the mean weight of state quarters differs from 5.67. Now you can also do confidence intervals, and I forgot about confidence intervals. Put it on here. Interval. Everything should be the same. So this is number 6. T test confidence. All we have to do is get rid of that. We are, oh, that's, actually, no, never mind. Run this again. Okay, but instead, we are going to use this confidence interval. This is what's great about t-tests. If you use that t-test, you have the raw data, you can do this. Otherwise, you got to do that. If you don't have the raw data, they give you the data, raw data, you have to test to find the confidence interval. Nice thing is this gives us the confidence interval. So since the confidence really just C, well, Here's our interval. 5, 6, 8 round. 5, 6, 8, comma 5, 7, 3, and 5.67 is not inside the interval. So we reject the hypothesis, and there you go. There is sufficient evidence at the 0.05 level at it differs. So isn't that nice? You just do one thing, t-test or, which gives you the probability, and you can do confidence interval. So nice, I like that. All right, so that's really all we have time for. It's 30 minutes for this whole thing, and it took me forever just to get it all set up. So I'm sure it'll take you quite a bit just to get all this typed in. We'll come back and do 4 and 10.5 for the next class. Maybe we just end here, because honestly I don't really feel like doing much more. And I think when I look at the final that was given to me from SLU, that says this is the final we're giving. With this right here, we're already doing more than they have at SLU. So I think we'll just stop here and 10.2 and 10.3 and not worry about the rest, because it's really the same thing. It's really nothing different than what we're doing with these. We do the same thing with proportion. Honestly, I just do confidence intervals each time. Is the proportion within the interval, or is the standard deviation within the chi-square interval? Honestly, if it is, then you fail to reject the null hypothesis. Everything's fine. If it's not inside the interval, then you reject the null hypothesis and everything's not fine. It is different than what it should be. All right. That's it, I think, for us. So your homework and your test or your final will go up to 10.3. We'll not go into 10.4 and 10.5. That'll be all for us. So starting next week, maybe next week or the week after, we'll have a final posted up for a week. Then we'll be done. All right.